So, yeah, hi, good evening. Today we'll start from the microstrip antenna. Before that, I want to ask, do you have any question or doubts from last week? Okay, okay. So let us go through this. So last week we ended it here. Like, what was the advantages of microstrip antenna? Why should we study microstrip antenna itself? Because nowadays we want miniaturized antennas and planar antennas, right? Because all these multiple applications, right? Like aircrafts or satellite and everywhere. It's better to have an antenna that will fit to the surface itself. So that is where microstrip antenna is very useful, and it gives you a moderate gain with a very small, feature. The size is very attractive here for microstrip antenna, and it is also robust, mechanically robust. Okay. Now let's see how the microstrip antenna looks like. We'll start the discussion on rectangular microstrip antenna. Okay. So in the right side, I suppose you can see it. It shows a rectangular antenna with the dimensions L cross W, where L is the length and W is the width. Okay. So this you must see carefully what is the length and width, because on that all the other aspects of the antenna will depend, like the field modes or the electric field, and magnetic field, current density, everything. The uh, direction of those, or vector direction of all the vector components, will depend on this. So our microstrip generally have a length of L and width of W. Okay. And you see the substrate, and below substrate we have the ground plane. Okay, it's a normal metallic ground plane, and it shows, in the picture it shows there are two radiating slots. So I suppose you have seen microstrip antenna before. Binay, did you see, Nandana?
Yes, sir.
Yeah.
Sir,
Okay. Okay. So can you visualize this radiating slots it is talking about? Can you understand what they are talking about by these radiating slots with respect to a microstrip antenna? What you have seen? So what are these?
Radiating patch slot in the sense.
Yeah. Yeah. So what are these slots? So here it shows this top patch. It has some thickness, right? Generally, if you see a normal fabricated hardware, the thickness is so thin that we don't consider it like this. A thick substrate we don't see. The in the picture right side, it has a top view and side view, right? In the side view, you see the thickness of the metallic patch is T. So this T is very thin. It's around 18 micrometer or 35 micrometer. Okay. But for all our microstrip considerations and all, we generally see it as a thickness, as a slot. All the sides of the patch, metallic patch on top of the antenna, we see it as a slot. Yeah. Now, do you understand what I'm talking about?
sir,
But
can you?
sir, but entirely it is same thickness. Now, why it is like slot one and slot two?
Yeah, that slot 1 and 2 has been specially mentioned because they are the radiating parts. There are like total
Okay.
4 slots at 4 sides, right? That you understand? Four
Yes.
slots. Yeah.
Yes.
Yeah. So out of that, only these 2 slots will lead to radiation, or will act as for the antenna. The other slots will not. That we'll look into later. But now you see how this microstrip antenna is considered geometrically. Yeah. Nandana? Yeah.
Okay, okay, sir. Okay.
Understood, right? The
Yeah.
top picture and bottom picture, top view
Mm-hmm.
and side view. Do you understand how they are seen?
Yeah.
Yeah, see the side view. The thickness is L. Sorry, the thickness is T
T.
of the T, small t, right? So
Mhm.
this thickness will be there in the four sides of the patch, right? So those are called radiating slots. Sorry, those are called slots of the patch
Slots.
antenna. Yeah,
Okay.
right. And you see the substrate and the ground plane there, right? So, and also with respect to that, in the right side, the radiating slot is described. If you take only one of the slots, uh, so you see, you note the directions. Okay, x, y, z. Do you see the directions x, y, and z? Okay, so along the y direction, along along the xy plane, xy plane is the our one of the slots. Is it clear? You see xy plane. Yeah.
Yes,
So
sir.
y is the perpendicular to this. So that means, sorry, this is xz plane. Xz plane is the plane of the radiating slot. Do you see the coordinates here? X, y, and z mentioned.
Yes, sir.
Yeah. So you see the slots. What are which plane is the slot in? No. What is the plane of the slots? The radiating slot is xz plane,
X
right?
and Z zipline. Yeah.
Yeah. So that is what is shown in the right hand side. So if you take a metallic cross section of the patch, that is only one slot, it shows as what would be the dimensions of this. It would be dimension of W into H, right? Because W is the substrate width, patch width, and H is the thickness of the this metallic thing. Okay. Yeah, H is the thickness of our dielectric substrate. So that's why the our radiating slot has a dimension of W cross H. W is in the direction of Z. W is in Z direction, and H is the substrate width. It is in the X direction. So that is what is shown here. Okay, so now we will go into these details, but let us first see how this length, width, height, and T, how they matters here for microstrip antenna. So these defined parameters are length of the patch, width of the patch, L and W. H is the substrate thickness, okay, and T is the thickness of the microstrip patch, and epsilon R, ER, is the dielectric permittivity. Are these defined parameters clear?
Yes.
Yes, sir.
Okay. So let's see. So microstrip antenna, the characteristics is the metallic strip is very thin. So metallic strip in the means the patch on the top of the antenna, that should be very thin. T must be less than lambda naught. And this T is generally what we take in normal our fabrication and all is around 18 micron or 35 micron. These are the standard dimensions taken. Okay, 18 microns means 18 into 10 to the power minus 6 meter. Okay, so that is how how thin it is. And the other characteristics is substrate height is also thin. So although it is not as thin as the T, but this H is also very thin. Generally, people take it around 0.003 lambda naught to 0.05 lambda naught. So it depends on the substrate basically and the wavelength of operation. And how do we design it? It says to maximize the pattern normal to the patch antenna. That means generally you want a broadside radiator. So normal to the patch antenna will be what direction? It will be, we want, now Nandana, tell me, in which direction do you want the maximum radiation from this patch antenna? Right side patch antenna drawing. Yeah.
Which direction means radiation pattern?
Yeah.
That is in the H plane.
So here X, Y, Z
Uh,
is mentioned, right? You tell me about this directions, X, Y, Z. In which direction?
uh, X is it? Where is it?
I am not talking about E plane, H plane. Only you tell me
Okay.
radiation pattern should be maximum in which direction?
Uh,
That is
if
what it says,
suppose,
right? Uh,
okay,
it says maximum normal to the patch or broadside
normal to,
radiated.
okay, yeah, okay,
So
okay.
which direction?
If
Binay?
suppose,
X.
X direction, right? Yeah, exactly. Okay. So that's why this is X direction is the normal to the patch. So we want a broadside radiation in X direction.
X direction.
Now let's say uh, what are the substrate? Generally, it says the substrate should be in the range of epsilon r. It can go from 2.2 up to 12. So it has it has quite a wide range of variation. We can take substrates of many different types. Like generally we use Arlon or Duroid or many different variations of Rogers. So yeah, like that, or FR4. So all these many different substrates are there. So we take we see how the epsilon r is and how is tan delta. Another thing generally we consider is the loss tangent. That is what is defined as tan delta. Okay, that also we consider. So how a good antenna? What are the parameters for a good antenna, patch antenna? So one should it should have high thick substrate. The edge should be large. Okay, so it should be a thick substrate and low dielectric constant. So dielectric constant epsilon r must be lower. Generally, it should be in the lower end of the range from 2.2 to epsilon r, and it should must provide better efficiency, larger bandwidth, and loosely bound fields for radiation into space. So you see, like the difference between microstrip antenna and microstrip circuit is that microstrip antenna it must radiate. Okay, so that's why the field must be loosely bound. If the substrate thickness is very thin, then what happens? The fields, the electric fields or magnetic fields between one metallic patch and the ground plane, they will be very tightly bound, right? So there is the fringing field will be very less. That is what we don't want. So that is required only in microstrip circuits. But in case of microstrip antenna, that's why we need a thicker substrate and lower dielectric. That will generate more fringing fields. And this fringing fields is the actual thing, the quantity that is leading to the transmission in microstrip antenna. Okay, so that is why in case of microstrip antenna we need a thicker substrate and lower dielectric constant, and it should be opposite for microstrip circuits. Is it understood?
So, sir, here fringing field is responsible for radiation.
Yeah, fringing field is the actual quantity responsible for radiation. Yes, and we want to generate more fringing field for better antenna characteristics. And how do we generate better fringing field? By increasing the thickness h or reducing the dielectric constant epsilon r.
The
Yeah.
fringing fields are those that are escaped to the air, no? That quantity is the fringing fields, right?
Yeah, right.
Okay.
If it does not escape to the air, how it will transmit, right? It has to radiate. Yeah. But in microstrip circuits, we don't want any radiation. We want the fields to be propagated within the circuit, not outside the circuit. That is where the difference lies between microstrip circuit and microstrip antenna. Is it clear?
Yes, sir.
Okay. Okay, now let's look into the fringing fields in details. Okay. So let's go back to our transmission line model. Let's see it as a microstrip circuit only, microstrip transmission line. So left side is shows a microstrip line of with W length L and all the other things. And you see the field diagram, how the field is like it goes fringes through the air and comes back to the ground plane. Okay, and generally the equivalent circuit what we see is that epsilon reference or epsilon effective permittivity of this medium composite medium of air and substrate is epsilon EF, and that is described like this. So it says the transmission line model yields, it does not give, better results. Generally, we look into a cavity model later, but why still we don't see into transmission line? Because, it gives you some physical insight. Let's see what are these insights. Due to finite W and L, the fields at the edges of patch undergo fringing. Okay, because of finite length. If it was infinite, length, there will be very few fringing. Because of finite only, it has this fringing effects. Now what happens? It is a non-homogeneous line, obviously, that we discussed, right? Because it has a interface between air and dielectric. That's why electric field lines reside in the substrate as well as in air. Now fringing makes microstrip line looks wider electrically compared to its physical dimension. So generally we have to take this all the fringing fields into effect. We consider a geometrically wider line. So W should be wider than this to take all the fields into inside the line. Okay. So that is what they say the effective dielectric constant is given by this formula is given. Now let's go to the others. Yeah, let's see. So now what happens? The formula effective permittivity of this medium is given that. So this effective calculation is very vital for all the microstrip line and antenna. Okay. What is this effective dielectric constant? It says dielectric constant of the uniform dielectric material. So the it's in the line of figure B, it has identical characteristics to that of normal figure. So we have a equivalent geometry here in the right side, figure B. Okay. So in the first case, what happens? Some field lines go through the air and some through epsilon. If we have a effective medium where all the field lines does not go into air, it stays within a particular medium itself. So that is what this epsilon are. Is it understood? What is effective dielectric constant?
So can you repeat once more?
So normal
Is it
temperature.
average like both dielectric constant? Is it the average
See.
value of both?
Bina repeat. Yeah.
Sir, is it the average dielectric constant of top like air and substrate?
No, it is not average. You see the formula? In only some cases, it might be average when H by W is very less. Okay.
No, sir. I'm asking like whether it will make the both mediums into a homogeneous condition by making
Yes,
average.
yes. Yeah, that is why we are having this constant at itself to make it look itself as a homogeneous medium. Although in reality it is not, but we are getting into, it is kind of like a homogeneous medium, but these are all effective medium or imaginary medium. Okay. It's not really actually.
Okay,
Nandana, is it clear? We have in normal microstrip line, we have some air and some substrate, right?
Yes,
But
sir.
that makes it what? Not inhomogeneous.
Okay.
And we cannot define only one epsilon r for this medium. But if we want a effective dielectric medium, that will encompass all the fields, all the fringing fields, everything into one medium, not two mediums. That's why this effective dielectric constant
Okay.
has been, calculated.
Mhm.
And this right side plot you see, this is a plot of epsilon effective versus frequency in log scale. Okay. So how it changes. So as the frequency of operation increases, most of the electric field lines will concentrate in the substrate only for higher frequencies. It will go into substrate, right? So that means the epsilon effective almost tends towards epsilon r. It becomes constant. Do you see in the right hand side? As the frequency increases, it becomes towards epsilon r. So only lower frequencies, this more fringing happens. So effective dielectric constant approaches the value of dielectric constant of the substrate. That means the homogeneous line of one dielectric, only the substrate. It becomes more homogeneous at higher frequencies. Okay. Okay. Now see, what are the other effective parameters of microstrip line or microstrip antenna? So because of these fringing fields, the length or width, they are all getting changed because the field is not now confined between the dimensions of microstrip antenna. It is going beyond the length or width. That's why we have now effective length. Okay. So you see the principal E plane, So now let's discuss what are the E plane and H plane for this antenna. Let us first look into. So do you remember what was the definition for E plane? That I would like tell you to remind. E plane was the plane having the electric field in one direction, electric field in the aperture. Okay, aperture of the radiator patch. It should have the electric field direction and also the direction of the maximum radiation or broadside radiation, where we want maximum radiation. So a E plane should contain two dimensions or two directions. One is electric field direction in the aperture and another is the direction of maximum radiation. So that should be E plane. Now you understand what should be the E plane in here. It is given as for this picture. What should be now? Let's ask Binay. Yeah, Binay, do you understand what should be the E plane for this patch antenna?
Yes, sir.
Yeah. So what
XY
would be the
plane.
electric plane direction? Yeah.
XY.
It is XY, but yeah, how is it coming?
Like because of the maximum radiation. I mean, as we
Maximum.
are desiring broadside radiation pattern.
Broadside radiation is okay, and yes. And how is the Y direction? Is X is the maximum radiation direction? I'm okay. And how is the Y direction is coming? It is XY plane, right? Yeah. How is the Y direction?
Y direction.
So it is written here E plane. That is what I have written, right? But how are you getting? For a let me give you another antenna. Can you from that can you determine what would be the any arbitrary patch antenna? What would be the E plane and H plane? How do you determine it?
The radiation pattern only.
No radiation pattern is required. From this picture only you can tell. That is what I'm asking. No, and it is very vital for any patch antenna. Anything you need to know what is the E plane and H plane, because everywhere people will ask. You see all the papers and radiation patterns everywhere in the book. They will give you E plane, H plane. So you must know what are the E plane. Yeah, you tell me what would the E plane should have. What are the any particular geometrical plane you can form out of two directions, right? X, Y, X,
Okay.
Z, whatever, two directions. So what should be the two directions here?
Two directions will be like electric and magnetic.
No.
Sorry.
What does the definition of E plane says? Yeah.
EX and EY.
No. That is not what it says. Let's go back. See, these are the basic things you must know. Otherwise, if you can have, all these big terms and all, that's all okay. You can read and learn. But the basic stuffs, you must understand what is it. Yeah. So for Nandana, is it clear for you? Can you tell what should be the E-plane?
Sir, E plane is the plane containing electric field vector and maximum direction of maximum radiation. So in our case, E plane is along
Here you see. Do you see
yeah.
this picture? Yeah, for the
Yeah.
yes. So E-plane vector
Yeah.
means what? Not the far field. It is saying E-plane electric field in the aperture of the
Uh,
antenna. radiating
okay.
aperture. Okay.
Mm.
Now from here you try to visualize for a horn antenna. So the outermost aperture of the horn antenna, it shows. Do you see, Binayak? Binay? Yeah.
Yes, sir. But in why it is intense?
Here you ask us what? Why it is?
In X it is maximum radiation. In Y, uh, in Y is E field.
We want broadside radiation, right? In the antenna only,
Yes.
our fabrication antenna should be having a broadside radiation. That is what we want. So from here, can you understand from this horn antenna? Why? What would be the E plane and H plane? Yeah, you tell me. What would be the E plane here? You see, everything is given here. You just have to clearly visualize.
E plane is towards Z, sir. Z and
H
Z
Which plane?
and
Which plane? Come again.
E
Which
plane.
plane? No, no, it's not clear. What did you say?
Yeah.
Nandana?
How is it?
Nandana, what is the plane
Yes.
of E plane?
One second. E plane is along Z and XZ, and H plane is YZ.
Yeah, so XZ is the E plane, right?
Yeah.
So how it is coming? You know, X is the direction of maximum radiation and Z is the direction of electric field. Is this clear from the definition? You know, see, definition only says the plane should have two directions. What are these two directions? One is the direction of electric field vector and the direction of maximum radiation.
Maximum radiation.
So electric field vector is the Z direction and the other side is X direction. And for each plane, it shows, you know, the magnetic field should be in the this direction, you know, in Y direction, and X is the direction. So XY should be the H plane. Is it clear?
Yes, sir.
Yes.
So now the question will come, why this electric field is in this direction? Why it is like this? Here this shows like this is the electric field direction and H, this is magnetic field. Why it is like that? How do you know? I don't know if you have, if you remember or not. So generally, the basic principle of the horn antenna is that it works as if like a rectangular waveguide. Okay, so for a rectangular waveguide, the main basic mode is TE10 mode. So for that mode, the electric field will be like this. The mode configuration of this TE10 mode in a rectangular waveguide is like this electric field aperture. So that is why it should be like this, and the magnetic field will be perpendicular to that.
Okay.
Okay. So, but okay, so this is the basic thing. But now we'll go to the patch. Now you should tell me from this definition. You must remember. Okay. Now let's go back to there and tell me there how the E plane and H plane comes there. Yeah. Now you tell me for our patch antenna what should be the E plane and what should be the H plane and why.
Maximum radiation. In Y plane it is electric.
Yeah. Tell me what.
In X direction it is maximum radiation, sir.
Yeah, and electric field.
Electric.
See, now the thing is, which portion I told you the electric field you should look into the radiating aperture. Okay. So in the top side patch, what did I tell you? Only the radiating slots they radiate. So you must see in the radiating slots what are the directions of electric field. Do you see the radiating slots? And the right hand side, it shows the electric field lines. Okay. So which direction is the field? Yeah.
Y direction.
Y direction.
No, is it clear, or you just written here XY plane, so you are saying XY?
No, sir,
Do you
that direction is showing towards Y.
in the left side picture only, the first left side picture, it shows the electric field
Yes, sir.
directions of radiating slot, right? So
Yeah.
radiating slot, what? It comes
Yes, sir.
out of the plane in Y plane. It is almost
Right.
perpendicular to the radiating slot. It comes out in the Y direction. Do you see it?
Yes.
Yeah. In the
Yes.
other side also, it goes into Y direction and enters the radiating slot 1. And slot 2, it comes out in Y direction. So that's why this is XY plane. Now you tell me what should be the H plane then.
H plane will be
XZ.
XZ.
Yeah, XZ, right. Because the electric field is in this direction, why each field would be in the Z direction. So that is XZ. Okay. So this you must remember. Okay. So because in every patch antenna, and not only patch, even other antennas also, E plane and H plane concept is very vital. So you must know this. Okay. Now let us go into see. So the equivalent circuit, it shows because of these fringing fields, they have a increased length, that is described as with del L. So del L is what? It gives you the extended length on the both side due to the radiating slots. Okay, because of fringing fields, we have a del L. So, and what should be the, if there are no fringing, the field mode is TM010. Okay, and the length would be generally around lambda by 2, and the resonant frequency is given by FR010 of this V naught by 2L epsilon R. Okay, so this field mode comes from a resonant cavity mode. We'll look into this, but for now you remember this. The main mode or dominant mode is TM010. Okay, and the length, you see, this is very vital. Generally, the patch antenna length L, it would be around lambda by 2. Not exactly, but it is close to lambda by 2. Yeah, so I hope you understand why it should be lambda by 2. You see the field configuration over the length is like in the one side is goes into in the upside direction x plus x direction. In the other side it goes into other minus x direction. So that is why, because it should be half wavelength, because in half wavelength only you have half variation of the wave. Because we need this kind of variation, that's why the length is required as lambda by 2. And the this delta L by H, this has a formula. It has been calculated like this in terms of epsilon effective and all. And with those, with increasing the age effects, you can calculate the resonant frequency of dominant mode as 2LF of all the other other quantities are also mentioned. Okay, epsilon effective and length effective, all this you should take into consideration. Then from that you can find the resonant frequency. So that means here it shows, as the length, effective length increases, the resonant frequency decreases due to fringing. Now, now you tell me what part do you not understand? Yeah. Do you understand how this effective length is affecting the frequency? This is one part. And second part is why L should be lambda by 2.
That as the effective length increases, the resonant frequency decreases.
Yeah, this is clear from the formula,
That is,
right? It is 1 by L effect. But you tell me, first you see why it should be like, L equals
lambda by 2.
Yeah, why it is required. You see this field diagram here. In the right side, the side view shows the field diagram, right? Field configuration. From that you see why should be like this.
Since it is opposite on two ends, means the field directions.
Yeah, so
No,
see, you are in right direction. For a good radiation, we need the field direction in opposite ends. Should be
Okay.
in same
Opposite,
direction.
same.
You see, both end it should
Oh,
be plus y, right? Plus
yeah.
positive y. That is what we
Mm,
told, right?
mm.
Electric field direction in the radiating slots, both should be positive plus y.
Mm.
You understand that, right?
Yeah, yeah.
Radiating slot 1 and radiating slot 2 both has electric field at positive y
Y direction.
direction. Because if it does not happen, if it is opposite direction, then the field will be in
Being
opposite phases and they will cancel each other.
cancels it.
That will
Okay.
not lead to any radiation. So that's why we want both of them in the same direction. And how that will happen? Because of if the wavelength, that the length between them, if that is lambda by 2, then this will lead to this kind of configuration. Because in lambda by 2 only, a wave goes through half wavelength. That will be this kind of same configuration that it shows here. So that's why L is required as lambda by 2. So whatever frequency you want to design your microstrip length antenna, your length should be around lambda by 2.
Okay, sir.
Yeah. Is it clear? Yeah.
Yes, sir.
Okay. So these are the, yeah. So what are the microstrip design procedure? Okay. So now I want you guys to look this very carefully and draw one antenna yourself. In the next my tutorial class, I will try to show you one, and you must also do yourself one and show me one design. Okay, one basic microstrip antenna design with these formulas. So see, so how do you start the microstrip design? So they say first specify what should be your epsilon r. Epsilon means what is the substrate you are having. Okay, so let's take something FR4. Okay, it has 4.3 dielectricity. And what should be the frequency range of your operation, and what is the thickness of your dielectric. These are the three things first mentioned, because these all are in your hand. Okay, because it depends on whatever the availability of the dielectric. So then what do? We determine the width of the microstrip antenna from this formula. Okay, and then we calculate the extension length of del L from this formula, del L by H, this. So from now with all this, we can calculate the actual length. So this length can be calculated as normal length, and we subtract the extended length. So generally this length is given as lambda naught by epsilon r. You see it is in the range of 0.47 to 0.49. Okay. So once if you know the epsilon r, fr and h, what do you want to need? What do you need is W and L, right? You need to know the W and L to design a microstrip antenna, width and length. Other things you already know. So how to calculate that? That is why it is given here. So now I want to tell you that in internet I found that there are very good resources from these websites. So please note down this and you compare between them. You see this resources Altium, these pages, EM Talk and everything RF. Both these pages you can actually calculate. If your epsilon frequency and H is given, they will calculate this L and W from that. So I want you to use their calculation and you also calculate using these formulas and see how it varies or matches. That for next tutorial, please look into that. So please note down these links. Yeah. And from these dimensions, please try to design a microstrip antenna in whatever CST, HFSS you have, you do that. Okay.
Okay, sir.
So yeah, you try one thing. You try FR4. Okay, substrate as FR4 and frequency at you try at let's say at 4 gigahertz. At 4 gigahertz and FR4 substrate you try, and thickness you take maybe it should be around let's say 1.5. Let's say 1.5 millimeter as the thickness. So with these three conditions, you start your design. Okay. 4.3 FR4 and frequency is this 4 gigahertz and height is 1.5 millimeter. So for that, you design a microstrip antenna. Okay, so let's go to the next slide. So the next discussion is how to feed the microstrip antenna. Okay, so just only designing the antenna is not enough. Obviously, you have to feed the wave. So what are the techniques for that? Let's see. So they say there are several techniques. One is contacting feed or non-contacting feed is the another. Contacting is is like microstrip line feed as shown in right hand side. You insert a microstrip transmission line itself to the patch. So that microstrip line is used to feed it. So it is easy to fabricate and simple to match and all this. It is a planar also. By controlling the inset position, inset position is exactly how much inside it enters into the patch antenna. By controlling that, you can match it. But generally, it has some problems in terms of bandwidth and all these things. And the other important method or very widely used is coaxial line feed. Okay, so how it is done is generally the microstrip is line like is that in the bottom side of the antenna on the ground side we make a hole or we make a via hole. Through that the central conductor of coaxial connects through the substrate to the top layer of the patch. I think this should be clear from the right side. See in the right side picture, right, bottom right. Okay, so top side is a circular microstrip patch. This is the top layer, and the bottom layer is ground. So you have to connect your coaxial connector in the bottom layer. So how do you do the coaxial connector? It has three layers. The first layer or inner layer is inner conductor. Then inside and we have a outer layer, outer conductor. In between you have a substrate or Teflon inside it. So three layers is inner conductor, outer conductor, and in between them we have a Teflon. So all those are in in concentric circles they are designed. Okay. So when you connect this coaxial connector, what happens? The outer layer of the coaxial connector touches to the ground, and only the center conductor that goes through the via hole and connects to the top patch. So this is also used very widely, and because microstrip line is designed generally for 50 ohm and coaxial also available for 50 ohm loads, so they matches very well. Yeah. So do you understand how this feeding works for both of these?
Yes, sir. Contact.
Yes, sir.
Okay. Okay. So now
So,
see. Yeah.
so where this inset is normally we used to keep it along the width, broader
Yeah.
section.
Yeah. Yeah. But
Why it is because of that radiating slots or
no, it is not that. Now
uh,
we'll look into that. When
okay.
you make it enter through the patch, it's called inset feed. Okay. So
Mm,
why that is so, that we'll look into that next slide. Huh? Okay.
okay.
Yeah. Now see what happens. Let's say you are talking about this kind of feed, right, Nandana?
Yes,
Here
sir.
it shows the feed. Yeah. Okay. Okay. So it shows. So yeah, all those this feeding and all. What is the important parameter is input resistance, right? Because we want maximum power should be transferred from feed to the antenna. So that's why input resistance is very vital. That is the parameter we should look for. Okay. So what it says, generally, this patch has two radiating slots. These two radiating slots, you can have an equivalent circuit like this. In the right side, you see the transmission line model. It has B1, G1, and B2, G2. Both of these comes from two radiating slots from the microstrip antenna. So each radiating slot is represented by a parallel admittance Y. So that comes from conductance G and susceptance B. It is modeled as a admittance circuit. Okay. So if that is the case, then equivalent admittance of slot 1 is the left side. it would be given as y1 equals g1 plus jb1. Okay, this admittance is just a summation of both of them. And similarly for the slot 2 also. Now the G1 and B1, how that can be calculated, it is mentioned in Balani's book through these formulas. Okay, you can actually calculate through this. If you know your parameters like H and W, all this, you can calculate. So now let's see how we can calculate the actual input resistance. Input resistance is calculated at which point? Where the feed connects to the antenna, right? That means radiating slot 1. Do you understand that? Radiating slot 1 is the left side and
Yes, sir.
radiating slot 2 is on the right side.
Right
Okay?
side.
Yeah, but we need input resistance in the left side. So now you see what it's saying. The total admittance at slot 1 is obtained by transferring the admittance of slot 2 to the other one. Okay, so we will calculate this as if the two resistances are connected. Two admittances of two slots are connected through a transmission line, and this length of transmission line is what? Lambda by 2. L equals lambda by 2. Okay, so that is why if we connect like this, then it would be the reverse. Okay, it will be having going through a admittance like impedance transformation. If you go through lambda by 2, you will have a impedance transformation or admittance transformation. So if you look if you look into the port 1 means radiating slot 1. So what should be the input resistance at port 1 for the slot 2, that is B2 G2? So that is given as Y2 equals G2 plus GB1, and it is going through transformed admittance. Why transform? Because it is connected through L equals lambda by 2. So that's why it becomes G1 minus JB2. The susceptance, it becomes opposite, negative. Because of lambda by 2, if you see the transmission line, the Zin equals JBL, we had a formula for transmission line, right? Input resistance. That if you look into, it will become like this. So that's why the total input resistance or total input admittance at the slot 1 becomes Y1 plus Y2. So Y2, the bar, Y2 bar is given for transformed, because everything we are looking from port 1, not from port 2. We are looking from port 1. That is our input port. So when you add G1 and G2, they adds up, and B1 and minus B1, they cancels. So that is why ideally they adds up to be a real part only. No imaginary part is there. Now you tell me what is not clear here. Do you understand how this input resistance is calculated here through these two radiating slots?
So input resistance is calculated at, it is actually a calculation of admittance, right?
Admittance,
No.
yes.
Yeah, that I understood.
How the main portion is transform of admittance of slot 2. That is what you have to see, because we have to look at port 1 only. That is input port.
Okay.
Okay, then let's go to the next slide. So now they're saying what should be the matching technique. If this is the, if you know the input resistance at port 1, so how we should match the transmission line to the transmission circuit? Because basically you should have 50 ohm matching, right? Then only maximum power should be transmitted. So the formula here, it says the input resistance, basically we calculated like, Z in equals 1 by Y in, so on 1 by 2 G1. Okay. So ideally it is 2 G1, 1 by 2 G1. So G1 is the, it is it comes from the first radiating slot and second radiating slot together. They are symmetric. Now what happens? there would be mutual coupling between all of them. So there should be the variation of G1 plus minus G12, and cos square, this variation is also there. So how this cos square length variation is there, cos variation. So let's see. So you see the equation, length and y equals y0. At y equals y0, what should be the case? At what should be at y equals 0? That is what we calculated here. Z in is the input impedance at y equals 0. That means left hand slot. At port 1 is y equals 0. But we want to calculate at y equals y naught in set feed position. What should be the input impedance at that point? So now see how you calculate that. We already know at y equals 0 it should be 1 by 2 G1 in this equation. Plus minus G12 is the coupling part that you can forget for the moment. And now how this cos variation is coming, let's see. So it says because of the length of our, the antenna, microstrip antenna, we have a lambda by 2 variation. So how is this variation cos variation? So it says microstrip antenna acts like a open-ended circuit. So both radiating ends, radiating end 1 and radiating end 2, these two slots acts like a open circuit. Okay, so open circuit means what? At the other end, at slot 2, it should have maximum voltage and current should be minimum. And same as the slot 1 also. Voltage should be maximum, current should be minimum. That is the condition of open circuit. So that means at the middle of the patch antenna, that means L equals L by 2, you should have a minimum 0 voltage and maximum current, because whole goes through lambda by 2 variation. So this curve, if you see plot, this is a cos square pi by L variation. It is a cos variation. Yeah, do you understand why how this cos variation is coming? Cos theta variation.
Yes.
Yes, sir.
Okay, so that is why the radiation input resistance at y equals y naught is given as pi by L y naught. You see the y naught term is coming here. So ideally it will be at pi by L y. So whatever at any y position, the length is the direction of y, that you remember. It is the y direction. So at any point in the microstrip patch antenna, you can actually calculate the resistance. Okay. So in the right hand side, it shows this actual plot, how it would be. So that shows in the right hand side, you have, it is actually, maximum. It is 1. It is a normalized plot. And the left hand side also, it is maximum. In between, you have point, it goes to 0. So we need what? We need at some point what is close to 50 ohm. Okay. Now from this formula, we can actually calculate at what point y equals 1. What would be the value of y naught such that the R in at y equals y naught should be 50 ohm. From this formula, we can actually calculate that. It all required for what? Because at y equals 0, what is 1 by 2 G1 plus minus G12 is not 50 ohm. If it is not 50 ohm, how we can calculate? We can go inside this antenna and then balance it so that it becomes 50 ohm. That is the condition of inset feed. Is it understood now, Nandana?
Yes, sir.
But sir, can you explain one more time this graph, normalized input resistance?
Yeah, right. See the in the equation here it shows what R in y equals y naught is related to R in at y equals 0. Y equals 0 is the first radiating slot in the left hand side. So if you normalize it, so what is left? Normalize R in y naught by R in y equals 0 is only cos square term is left. So that cos square term has been plotted here. Okay, so this plot only shows the cos square theta term. So what would be that? How it varies with pi by y naught by L. Okay. Yeah. So it shows that most of the time at the left hand side or at slot 1, that is y equals 0, it is not 50 ohm, but you have to balance with 50 ohm only. So then how do you do? If you go inside at some point, it would be 50. That is why you should take a inside feed. And how does it physically mean? What is physically means? So I said inside feed introduces a physical notch. Okay, notch means you are cutting some portion of the antenna, and it introduces a junction capacitance. You see there are there's a air substrate gap between the microstrip line and the patch antenna. This acts as some capacitance. So this actually it affects the input resistance, and also bandwidth. Everything is affected through that capacitance. Okay, this is the actually physical significance. If the resonant frequency changes, then the input resistance also changes.
Is there any condition for that gap also? The feed and
Uh,
patch?
yeah, this gap generally it does not have a formula here. You have to generally see to balance your the bandwidth and everything. You have to do several runs and tune it. The tuning is required. But main parameter is the y naught. At what gap you have the input, real part of your resistance in input resistance is 50 ohm. The y naught parameter is mainly important. How much inside you should go. So what you should do for your is tomorrow next week's tutorial, that you try with this antenna and this defined y naughts and different values of this cut. For the junction capacitance, how much gap is there, that also you vary and see how it changes, how it affects your calculation, input resistance calculation. You plot the input resistance with that defined take a parametric run and see it. So until you do it yourself, you will from theory you will not learn that much. Now let's go into next. So we'll start from the cavity model. I'll take 1-2 minutes break. So you guys can also take some break. Okay, I'll come back after 1-2 minutes. Okay. So yeah, are you guys there? Yeah. Should I continue?
Yes.
Yeah.
Sir.
Okay. Okay. So should I? So yeah, the last few slides we mostly looked into transmission line model. Okay, how the transmission line model we can use to analyze microstrip antenna. But the main model what people generally work on is the cavity model. So yeah, so this is the last part of our discussion is cavity. So I think you have studied in your BTech electromagnetics some portion is how a resonant cavity works. Okay, it is a variant of the waveguide where all three sides of the waveguide is blocked. It has metallic layers in 3 dimensions. It is a volume or like any substrate enclosed by a PEC or metallic layer in all 3 sides, every sides. Okay, so it is like a metallic cube, and inside that metallic cube we have substrate. That is generally the configuration of a cavity, rectangular cavity. Okay, so how that resembles here? You see here what happens. The microstrip antenna, the top layer is the metallic antenna, metallic patch, and the bottom also we have a ground layer. Okay, in between we have the substrate. So what people have done is that they compared this as a cavity, and we will look into is how it is helpful. How so generally we can all calculate the frequency modes or electric fields and all this, and also even not even only that, even the radiation pattern we can almost exactly calculate through this cavity model. That is why it is very immensely it is so much important. You can from this equation only you can analytically calculate the radiation pattern of this microstrip antenna through equations, not through any measurement or anything, any simulation. So it almost matches with the simulated pattern or measured pattern. That's why this cavity model is almost exact. So now let's see how this is. In the right hand side, you see it is actually a dielectric, looks like a dielectric loaded cavity. So in the top and bottom layer is the metal, and the other sides we see how that also it look kind of works like a metallic layer that we'll see. So in the right in the picture you see these are the charge diagrams. They show if the wave propagates, then what would be the charge electric charges, positive and negative, how they will how would be the configuration, and for that what would be the direction of current flow. Current density is given as JT is the top layer current, JB is the bottom layer current. Okay, that is what how it is shows. JT and JB, top and bottom layer of the patch, metallic patch. So because the length of this is around lambda by 2, it shows around it shows the variation of positive and negative. One at one side is positive, another side is negative because it's lambda by 2. It's opposite. And the same thing happens in the bottom layer also, positive and negative in the other sides. Now see, this says that normalized fields within the dielectric substrate. Now because of these charges at top and bottom, there will be electric fields from top to bottom, right? It can be found by treating this region as a cavity bounded by electrical conductors. So what are the conductors? Above the cavity, above the dielectric and below the dielectric. Okay. So when the patch is energized, a charge distribution is established on the upper and lower surfaces of the patch. That is what it shows with plus and minus signs, as well as on the surface of ground plane. Even on the ground plane also it shows some charge direction. Now says because this charge direct distribution is controlled by two mechanisms. So it has been studied. There are two mechanisms for this charge distribution. One is attractive and another is repulsive. What are these two? Let's see. So the attractive mechanism, it says, is between the corresponding opposite charges. Obviously, who attracts, only opposite charges attracts each other. Between the opposite charges on the both side, plus and minus, they will, attract each other, and that will lead to current flow, right? So if the charges moves, then only this current flow comes. And the repulsive mechanism is between the similar charges on the top and bottom surface. You see there is positive in the top surface and positive layer charges also on the ground layer. So that will lead to repulsive mechanism. Now the movement of charges create the current densities JB and JT. So JB is the the bottom layer charge and current flow, and JT is the top layer current flow of patch. Yeah, until this, is it clear? How do you see this? How the charge and all everything is lead to current flow in the patch.
Yes, sir.
Okay, sir.
Okay, so this is very vital, because in the if you see the hardware, all are very tiny layer, but with that only people have looked into. Although in the picture it looks like very big surface, big volume, but actually physically it is very small, tiny portion. But it has been analyzed like this. Okay. So it says most practical microstrips, the height to width ratio is very small. The generally the height of the substrate is very small compared to the width of the patch. So that will lead to what? That says only the attractive mechanism will dominate, because this the distance between them is larger. The repulsive mechanism does not dominate. Only the attractive mechanism dominates. That means only this current flow will lead to only between the surface, we between the positive and negative. That's why the JT becomes almost zero. Most of the charge concentration and current flow remain underneath the patch. Only it remains below the patch. JB is only the relevant charge density, and JT almost becomes zero. Okay. So that says because of this, only attractive mechanism dominates, and the current flow will become between the positive and negative charges below the patch and microstrip patch antenna. That is the JB component. And the JT component comes from the repulsive mechanism. It almost becomes zero. So in the top of the patch, there is almost no current flow. That is what you should remember, because later we will use this. Okay.
Sir,
Yeah.
this
Is it clear? Yeah. Yeah.
sir, JT will also appear in negative side also, no?
JT will appear. Yes, yes. That will be there. Yes. Generally, you see the direction of JT. It goes, because of repulsive mechanism, it goes from the bottom towards the up. Okay. That's the, the direction it shows. Okay. From the bottom towards up. Even the same thing will happen for the negative charges also. Okay. So because of repulsion between the positive charges, they go from one bottom to the top of the patch. Okay. But it says because of the geometrical configuration of microstrip, because the height to width ratio is small, that's why this repulsive mechanism is almost negligible. That's why JT becomes zero, and JB is the significant component, and JB lies in the bottom portion of the patch. Okay. Now let's see how it is helpful here. So it says, with all this charge model and current flow in our account, now we see we have a equivalent circuit here, equivalent cavity. In the right side, you see this is our cavity. So it shows the patch antenna, only the metallic portion. It has the length L, width W, and thickness of H. So that this is a metal resonant cavity, which has the top layer and bottom layer as metal, and in between you have the substrate. Yeah, do you see the how we get a metallic cavity here from our patch antenna? Do you understand this? In the right hand side, it shows the equivalent diagram of a metallic cavity as obtained from our microstrip patch antenna. Nandana, yeah, is it clear?
Yes, sir.
Okay, so is you must see that top layer and bottom layer is the metal, and yeah.
Sir, actually, transmission model and cavity model is same, no? Means from the same model?
No, it is
No.
different. This is cavity model. This
Same means actually on the top layer it will be any metal, and in and bottom will be also ground or some metal, and in between substrate. So from that basic model only both these two are designed. No?
But here you see we are ignoring the other portion of the substrate. We are taking only the metallic layers. But in the patch antenna, there are
Okay, okay.
substrate on the beyond the metallic patch also. Patch is very small also, right?
Yeah, okay, yeah, that's
Outside the patch there is substrate that we are ignoring. Only the
okay.
substrate we are taking
In
between the
between that.
metallic.
Okay.
Now let's see what it happens here. So says in the practical microstrip antenna, height to width ratio is very small. Okay, so that's why the current flow around the edges of patch. Around the edges means this in the four side walls. Four side walls is the edges. Okay, and top layers is the metallic layer, top patch layer and the bottom ground layer. And other than these two, there are other four layers. These are the side walls. Okay, what we called before, these are slots, right? Two of these are radiating slots, and other two are not. These are also side walls. You can look as side walls of the metallic cavity. So it says current flow around the edges of the top patch to its top surface become almost zero. So very negligible current flow between the on these four slots. Okay, current density means JS, surface current density, because of very negligible thickness. So if the current density is zero, now the tangential magnetic field, if you remember the boundary condition, neta cross H is given as what is the JS. The boundary condition says the current density will be related to the tangential component of tangential component of magnetic field. So if this current density is zero on the side walls or slots, that will lead to no tangential magnetic field component. Do you understand this?
Yes, sir.
See, yeah, now here comes the definition of PEC and PMC. I think you have also heard maybe perfect electrical conductor and perfect magnetic conductor. Now see, perfect electrical conductor is very, this table I have shown here, it is from the Balanis electromagnetics book. Okay. This everyone knows and it also exists in reality. But PMC or AMC, artificial magnetic conductor also, sometimes it is called, it in reality does not exist. But it is required for all this analysis and all. Okay, that's why you are talking about this. Now see how this PMC and PEC comes. So yeah, I will ask you, for a electrical conductor, what are the conditions? What are the boundary conditions? Yeah, you tell Binay. What would be the boundary conditions for electrical conductor in terms of tangential fields or whatever? Yeah, all this.
So for electrical conductor,
What would be the boundary conditions? You know boundary conditions, right? From basic electromagnetics.
like magnetic wall, electric wall, those.
If you take a metal, what should be the tangential electric field and tangential magnetic field on a metallic conductor. You tell me that. That is the boundary condition, right? This is the basic electromagnetics, right? You must have studied in third year or second year of basic bachelor's degree. Nandana, do you remember?
So for PEC, tangential electric field must be 0.
Okay, and tangential magnetic field?
It must be continuous.
Continuous? Yeah, it is. Yeah. And it should be related to what? The current density of the
Current
surface.
density
Right?
of the surface.
Exactly.
JS.
Right. And the other components like perpendicular components would be also related, but they won't be 0. Okay. Yeah. So the main important point is for an electrical conductor, the tangential electric field should be 0. Okay. That is what is important. Now the thing is for perfect magnetic conductor, it should be opposite. So perfect magnetic conductor should have tangential component of magnetic field should be 0, not electric field. And tangential component and electric field is non-zero. Is it understood? Difference between PEC and PMC?
Yes, sir.
Okay. So now see how this is important. I told you for our cavity what is happening, there is no surface current. That's why it is going to lead to 0 tangential magnetic field. If there is no surface current, obviously no magnetic tangential field will be created on these slots, the 4 side walls. So that's why these 4 side walls can be modeled as PMC, perfect magnetic conductor. That is the main point of our cavity model. The side walls can be considered as PMC, perfect magnetic conductor, because there is no surface current, and that's why there has 0 tangential magnetic field. Okay, and the top and bottom layers is PEC, and other 4 layers is PMC. That is how it is, actually analyzed. Did you understand? So, in a cavity, you have 6 layers or 6 walls. 2 layers is PEC and 4 layers are PMC. Yeah. Do you understand this? Is it clear?
Yes, sir.
Yeah. I hope you got what are the 4 layers. Yeah. I mean, what are the 4 side walls? Yeah. So top side walls is now you see in terms of X, Y, Z. So YZ plane is the top and bottom layers. This is PEC, and PMC conductors are in which layer? XZ, XZ and XY.
XY.
In XY direction we have XY plane we have two PMC.
2 side walls.
2 side walls. Those are PMC surfaces, and also in XZ also we have 2 layers, 2 PMC layers. Okay.
Yeah.
So so maybe I will stop it here. So from tomorrow on, we will start it here from fringing fields. How this is important for the cavity model and all the other stuffs. Okay. So you go through all this, and maybe you try to simulate one of these antennas from the these previous equations, and the pages also, and you must go through this inset fit thing. You should see how this Y0 affects your input resistance, that you must note. Okay, this is very, very important. This you see, and also the microstrip design. You must design one at FR4 4 gigahertz and 1.5. Okay, so you see how that is simulate one and see it. Okay, so that's all for today. We'll meet you tomorrow.
Bye.
Bye.